Chapter 7. Let us study some more facts related to light and its brightness in nature in the chapter Wonders of Light, Part 2. Let us study about refraction of light. Let us do this activity. Take a heavy rubber ball. Keep it in water in a tumbler. What change do you observe in its size when viewed from the sides? Take a beaker filled with water. Insert a pencil in vertical position in water such that a part of the pencil is inside the water and remaining part is in air. What change do you observe in thickness of pencil? Now place the pencil obliquely in the same beaker. What do you observe? Light travels along a straight line path in a transparent medium, but it does not travel in the same direction in all media. When it travels from one medium to another obliquely, the direction of propagation of light in the second medium changes. It is the phenomenon of refraction. The phenomenon of change in the direction of light when it passes from one transparent medium to another is called refraction. The direction of light rays changes when it enters from one medium to another as the velocity of light is different in different media. Appreciation of the refraction. Let us look at another activity. Let us look how refraction takes place through a glass slab. Take a sheet of white paper on a drawing board using pins. Place a rectangular glass slab over the sheet in the middle. Draw the outline of the glass slab with a pencil and label it as PQRS. Draw a line AB inclined to side PQ of glass slab. Line AB meets side PQ at N. Fix the pins on this line A and B at any position. Through the opposite edge of the glass slab, look for the images of pins A and B. Fix two other pins, say C and D, in such a way that images of A and B lie on a straight line with C and D. Remove the pins and the slab. Join the positions of tips of pins C and D by a line which meets at N to side SR. Join N and M. Also produce AB up to X as shown. Ray AX gives direction of incident ray. What is your observation about the emergent ray and direction of the incident ray? Refraction of light takes place twice in the glass slab. The first refraction takes place at N on side PQ, when the ray of light enters from air medium to glass medium. The second refraction takes place at M on side SR, when the ray of light enters from glass medium to air medium. The extent of change in direction of the ray of light at the opposite parallel faces PQ and SR of the glass slab is equal and opposite. Due to this, the ray emerges parallel to incident ray, but the light ray is shifted slightly to the left side. Why does this happen? Here, refraction of light has taken place because light has passed from one medium to another, so change in direction of light is seen here. Let us look at the laws of refraction. 1. The incident ray and the refracted ray are on the opposite sides of the normal at the point of incidence, and all three lie in the same plane. 2. For a given pair of media, the ratio of the sine of the angle of incidence to the sine of the angle of refraction is constant. If I is the angle of incidence and R is the angle of refraction, then sin I upon sin R is equal to constant. This constant is called as the refractive index of second medium with respect to the first medium. It is denoted by this letter. Refractive index. The extent of change in the direction of the light ray is different for different media. It is related to the refractive index of medium. Refractive index for different media is different. Values of refractive indices for some media with respect to vacuum are given in this table. The refractive index depends upon the relative speed of propagation of light in different media. Consider a ray of light traveling from medium 1 to medium 2. Suppose V1 is the velocity of light in medium 1 and V2 is the velocity in medium 2. The refractive index of the second medium with respect to the first medium is given by the ratio of the magnitude of velocity of light in medium first to that in medium second. It is represented as 1n2. Similarly, the refractive index of the first medium with respect to the second medium is given in this way. If medium first is vacuum or air, then refractive index of medium second is considered with respect to vacuum. It is the absolute refractive index of medium and represented as N2. When the ray of light moves from an optically rarer medium to an optically denser medium, then ray bends towards the normal. Example, from air to glass. In this case, the refractive index of the second medium is greater than the refractive index of the first medium. The greater is the value of refractive index, the more is the bending of refracted ray towards the normal. The angle of incidence is greater than the angle of refraction. When a ray of light moves from an optically denser medium to an optically rarer medium, the ray bends away from the normal. Here, the refractive index of the first medium is greater than refractive index of the second medium. The greater the value of refractive index, the lesser is the bending of ray away from the normal. The angle of refraction is greater than the angle of incidence. A special effect is observed when the ray is incident normal to the interface between any two media in any way, that is, either from rarer to denser or denser to rarer medium. Here, the angle of incidence is 0, hence ray of light propagates undeviated from one medium to another. Have you heard about mirage? You might have observed it on a very hot summer day in the afternoon. It is the apparent random wavering of the hot air rising above the heated roads. Also, at the time of Holi, you may have seen flickering of an object through a turbulent stream of hot air rising above the holy fire. The air just above the fire becomes hotter than the air further up. The hotter air is lighter and rarer than the cooler air above it, which is denser. Hence, the refractive index of hotter air is less than refractive index of cooler air. As the physical conditions of air are not stationary, the apparent position of object fluctuates. It is the effect of atmospheric refraction on a small scale in our local environment. The large-scale effect is the twinkling of stars. The stars emit their own light and they shine at night. The stars are point sources of light that are very far away. During refraction of starlight from the atmosphere, as starlight bends towards the normal, the apparent position of the star is slightly higher than its actual position. Also, this apparent position of the star is not stationary but changes slightly. Because of mobility of air and changes in the temperature, the atmosphere is not steady. Hence, refractive index of air in the given region goes on changing continuously and randomly. When the atmosphere refracts more light towards us, the star is seen bright. When the atmosphere refracts less light towards us, the star is seen dim. Thus, due to change in refractive index of atmosphere, stars appear twinkling at night. The rays of light from a planet also pass through the atmosphere of the Earth. But planets do not twinkle. As compared to stars, planets are nearer to the Earth. So a planet can be considered as a collection of a large number of point sources of light. If the intensity of light from one point source decreases, it increases from the other source. Hence, average intensity remains the same. Therefore, planets don't twinkle. Similarly, advanced sunrise and delayed sunset can also be explained on the basis of atmospheric refraction. The observer should see the sun when it reaches the horizon, but it is seen 2 minutes before that. As a ray of light from the sun enters the Earth's atmosphere, it follows a curved path due to refraction before reaching the observer. It appears to the observer as if the rays are coming from the position where the sun is seen by the observer. Hence, the sun is seen earlier before the sun reaches the horizon. Hence, advanced sunlight and delayed sunset increases duration of day by 4 minutes. Think why. 1. Water in a swimming pool or water tank appears shallower than its depth. Answer: 1. We can see the bottom of the pool because of the light rays coming from it. Light rays coming from the bottom go out in the air. 2. They get refracted from the normal. 3. The rays meet at the point in the water from where virtual image of the bottom of the pool is created. 4. Thus, water in a swimming pool or water tank appears shallower than its depth. 2. Place a coin at the bottom of glass jar containing water. Now tilt the jar suitably. When viewed at a suitable angle, coin appears to be floating. Answer: 1. The coin under water appears to be floating when we tilt the jar due to refraction of light which takes place when it goes from water into air. 2. When we tilt the jar, the rays coming from the coin travel in water in straight lines until they reach the surface of the water. 3. When these rays go out in the air, they get refracted. 4. They bend away from the normal and enter our eyes. 5. Virtual image of the coin is formed. 6. Thus, coin appears to be floating. Let us learn about dispersion of light. Look at this activity. Take a plastic tub. Fill it with water up to 2/3 of its capacity. Hold a small mirror in the inclined position in water. By using a torch, allow the white light to get incident on the mirror inside the water. Adjust the angle of incidence of light so that you can see the reflection of light on the nearest wall. What do you observe in the reflection? In this case, splitting up of white light into different colors takes place. The various colors obtained after splitting are in the sequence violet, indigo, blue, green, yellow, orange, and red. The acronym VIBGYOR can be used to remember the colors. The phenomenon of splitting of light into its component colors is dispersion. The band of colored components of a light beam is called its spectrum. Sir Isaac Newton was the first to use a glass prism to obtain the spectrum of sunlight. A prism is a transparent medium bound by two plane surfaces inclined at an angle. When white light is dispersed into 7 colors by a prism, different colors of light bend through different angles with respect to incident ray. Out of these 7 colors, red light bends the least, while violet light bends the most. So the rays of each color emerge along different paths and become distinct. Hence we get a spectrum of 7 different colors. Let us try this activity. Take a prism. Allow white light to fall on it. Obtain a spectrum. Take a second identical prism. Place it parallel to the first prism in an upside-down position with the first prism. Allow the colors of the spectrum to pass through the second prism. Obtain the beam of light emerging from the other side of the second prism. What do you observe? What is your conclusion from this activity? The above activity is an experiment performed by Newton which led to an idea that the sunlight is made up of 7 colors. In this case, dispersion produced by first prism is equal and opposite to that of the second prism. The beautiful phenomenon of the rainbow is a combination of different phenomena: dispersion, refraction, and reflection of light. The rainbow appears in the sky after a rain shower. The water droplets act as small prisms. When sunlight enters the water droplets present in the atmosphere, they refract and disperse the incident sunlight. Then they reflect it internally inside the droplet and finally again refract it. As a collective effect of all these phenomena, the 7-colored rainbow is observed. Let us study scattering of light. Take 3 beakers and number them as 1, 2, 3. Make a solution of KMnO4 in water in beaker number 1. Add a few drops of ink to the same quantity of water in beaker 2. Add some wheat flour to the same quantity of water in beaker 3. Stir each solution properly by using a glass rod. Direct a beam of light from a torch through these beakers 1, 2, 3. In which beaker is the path of beam of light visible? Why? The path of beam of light is visible in beaker 1 and 2 because when light incident on very small particles in the solution in a transparent medium is scattered, we can see the path of light. In which beaker the path of beam of light is not visible? Why? The path of beam of light is not visible in beaker 3 because when light incident on very small particles in the solution which is not transparent do not get scattered. We have studied Tyndall effect before. When a ray of light is incident on extremely small particles, the particles deflect the light in different directions. This phenomenon is scattering of light. Similarly, when a parallel beam of light is incident on a plain polished surface like mirror, the angle of incidence is the same for all the rays, and so we get a parallel beam after reflection of this light. But when the same parallel beam of light is incident on a rough surface like bricks, walls or ground, the angles of incidence are different for different rays of the beam. Hence, the reflected rays travel in different directions, leading to scattering of light. The scattering of light takes place through the atmosphere, as the atmosphere is a homogeneous mixture of minute particles like dust, smoke, tiny droplets of water and molecules of air. When the sunlight passes through a canopy of dense forest, scattering of light can be observed. The size of scattering particles plays an important role related to the color of scattered light. Very fine particles mainly scatter blue light. Particles of larger enough size can scatter white light also. In the visible range of light, maximum scattering of blue light and the least scattering of red light takes place. As red light is scattered the least by atmosphere, it can travel larger distance. Hence, danger signals are red-colored. Let us look at one more activity. Take drops of watercolors in the following proportions and mix them together. What is the resultant color obtained? We get blue color on mixing it. Blue color of the sky is related to scattering of light through atmosphere. The molecules of air and other particles of atmosphere have very fine size as compared to the wavelength of visible light. When sunlight passes through the atmosphere, these fine particles scatter light of different wavelengths in the same proportion of wavelengths of red, orange, yellow, green, blue and violet colors. Thus, red, orange, yellow do not scatter much by the air molecules and pass straight through. The shorter wavelength blue light scatter all around the sky by air molecules in the atmosphere. The scattered resultant light enters our eye and the sky appears blue. When astronauts fly at higher altitude, the same sky appears dark to them. This is because there is no atmosphere at high altitude and so the scattering of light does not take place. Even though the sky looks blue, it appears reddish or orange at sunrise or sunset. This change is also related to the scattering of light. At the time of sunrise or sunset, the sun is very close to the horizon. Sunlight has to travel a longer path through the atmosphere to reach the observer. The blue and violet color are scattered in a greater amount than red color. They are scattered away from the path of light as thickness of the atmosphere is more between the horizon and the observer. The light that reaches the observer is mostly red and yellow. Hence, the color of the sky is reddish-orange. Let us look at one more activity. Place a strong source S of white light at the focus of a convex lens L1. This lens is useful to get a parallel beam of light. Pass these parallel rays through a transparent glass beaker containing clear water. Place a cardboard having a hole after the beaker. Also arrange a second convex lens L2 and screen as shown in the figure. Switch on the source of light and by adjusting the distance of second lens and the screen, observe a sharp image of the circular hole on the screen. Now add 25 gram sodium thiosulfide in 250 milliliters of water in a beaker and add a drop of concentrated sulfuric acid in it. What do you observe when you look from the sides of the beaker? From the three sides of the glass beaker, blue light is observed as the colloidal particles in the solution scatter the blue color. The color of the image on the screen becomes crimson red. This is because the red color of the beam of white light mainly reaches the screen through colloidal solution. Students, do you know when and why we celebrate National Science Day? Dr. Chandrasekhar Venkataraman announced his work on scattering of light on 28th February 1928. For his outstanding work, he got the well-known Nobel Prize in 1930. He was the first Indian scientist to get the Nobel Prize. Government of India celebrates this day, that is 29th February, as National Science Day. Well, that ends the chapter. Hope it was a joyful learning. You have the options to view a mind map for a quick recap and a question and answer section to study the exercises. Wish you all the best. Bye till we meet again.